So there was a follow-up question on whether under certain under certain special cases you could have stress tensors evaluating to the same numerical value. This can happen under special states of deformation. It may be of a little use to, of some use to look at what happens with uniaxial deformation, okay, or uniaxial tension. Okay, so let's look at the stress tensors. For uniaxial deformation. Okay, so let's recall the picture. Okay, let's make sure that this is E1, E1, this has to be E3, and that is E2. Okay, let's do the reference configuration. Okay, this is omega naught, and we have a force F as we wrote originally. Okay, cross-sectional area pi r square and length capital L. Okay, this undergoes deformation, gets nice and elongated. Okay, the force remains the same. This is omega sub t pi little r square, and that length is little l. Okay, so let's just write out all the stress tensors, right? Easy enough to write are P, okay, because P is just, let me note now somewhere, let me note maybe just above this, let me note that F, the way we've written it is F E1, okay? Right, that's F without the underbar is just the magnitude of F. Okay, so then what we see is that P equals little f over pi r square E1 tensor E1. Sigma is little f over pi little r square E1 tensor E1. Okay, what about F? Okay, remember F is the deformation gradient. Okay, it gives us in this particular case, F can be written as, if you think about it, F turns out to be the following, right? We can just write F in terms of each of the stretches, right? So each of the stretches give us the following. Along the E1 direction, we have little l over capital L, E1 tensor E1, plus along the other two directions, we have little r over capital R, E2 tensor E2, plus E3 tensor E3. Okay, right? Now, of course, we noted that there was a relation. If this thing is incompressible, let's assume that it does it have to be incompressible? Well, it doesn't have to be. If we make it incompressible, we need to introduce some other conditions there. So let's not assume that it's incompressible. Okay, it is compressible. Okay, what we can do now is right. So this is F. Now note some things. though I said that in general it did not make sense to ask if P were symmetric, this is a case where P is indeed symmetric. This is also a case where it's just the matrix that we would compute for P which turns out to be symmetric. Okay? If you think back to my answer to the previous question, the fact that the force has the spatial nature whereas the reference area has this reference nature still says that there is no physical significance to this quantity being symmetric. There is, however, physical significance to this quantity being symmetric because it implies the balance of angular momentum. All right? Also note that once again in this case, F is symmetric. Okay, it's not usually the case, right? So even though F admits this decomposition of RU, okay, this is a case in which R is the, what is R? Is there any rotation here? No. So R is just the isotropic tensor. Okay, and in fact U is the same as F in this case. Okay, special case. But what about the Kirchhoff stress? Okay, J sigma. Now J is final volume over reference volume. Sorry. Okay, F over pi little r square, okay, E1 tensor E1, okay, because this is sigma. All right, so in this case, what do we see? We see that we get L over pi r square L F E1 tensor E1. And then we observe that actually when we combine these guys, right, we see P lurking in there. So this is actually little l over capital L P. All right. And finally, what is F inverse? F inverse is L over L E1 tensor E1 plus R over little r E2 tensor E2 plus E3 tensor E3. Okay, S, which is F inverse P, is L over L, it's all of this stuff, right? E1 tensor E1, I'm going to write this out in detail so we see how things work out, plus R over R, E2 tensor E2 plus E3 tensor E3. Okay, all of this is F inverse acting on P. P was F over pi capital R square E1 tensor E1. Okay, so all of this is F inverse and this is P. So now when we put things together, we see that because of the fact that E1, E2, E3 form an orthonormal set, any action of E2 or E3 on E1 is going to drop out, okay, because of the orthonormality. And the only thing that survives then is F capital L over little l pi capital R square E1 tensor E1. Okay, this is S. So now if you look at S here, you look at tau here, right? This is tau. Right? And we look at sigma and p. Let's just write them all again, just so that we see what all the relations are. Sigma is f over pi r square E1 tensor E1. Okay? P turns out to be r square over capital R square sigma. Sorry, I butchered this R. Okay? Tau tends to will become, what did we see? We saw that tau was well, we related it to capital P. Okay, so tau was little l over capital L P, which is what is it? It is now L R square over capital L R square sigma. And finally S we found to be okay, we found F to be S to be capital L over little l P. Capital L over little l P, which is right, it is L R square over L R square sigma. Okay, so there you have all the stresses in terms of sigma. So they're all similar, they're just different by they're just scaled differently. Okay, and this is all because we have uniaxial deformation here, and then it is just the effect of the change in volume, the change in length and radii, which gives us different magnitudes for these stresses, right? But their orientations are all the same.